All right. Good evening, everybody. Can you all hear me okay?
Yeah.
Yeah? All right. Loud and clear? Wonderful. Let me just turn up the volume so I can hear you guys a bit better. All right, let me see. We got 1, 2.
Why are you in Kevin's room, Justin?
It's a long story. My computer doesn't work as well as his, so I'm using his computer today. Just his last time. And I have come to a mutual agreement with him that between the hours of 8:30 and 10 o'clock, I will not look up anything bad on his web browser.
Please do it without him noticing.
And I'll share the screen with you too, right? All right, so it looks like I'm at 9 people, including algebra, including me. 1, 2, 3, there we go. Admit everyone. So we're at 10. 1, 2, 3, 4, 5, minus 5. All right, we'll give it another minute or two. How's everyone doing today? Good. Both 2 thumbs up? Great. And I'm juggling between screens again. Let's pin my screen so you can see me clearly. I'll run a couple minutes. Asian Standard Time, give them a little slack. Kevin doesn't look too happy again. Admit. All right, welcome back, Aaron.
Hi.
Hi.
Did you miss me?
Yeah, I always miss my students when they're gone. I like big classes with a lot of people.
Justin, you have another copy of yourself in the Meet?
Oh yeah, that's okay. I keep it there so I can see how clear my screen is when I start to write. So whatever you guys see, I see. Because how it works is I'm hooked up to a camera right now, but the camera is always clearer on my screen than it is on your screens. So I do it to see how. Yes.
It's pasta and salt.
Oh, hey, are you saying I thought it tasted just fine. Kevin's complaining about my cooking again.
Yeah, you're wrong.
It was better than yours. All right, it is 8:34. It's 8:34. We'll get started. Welcome and congratulations. We all made it to lesson 5. Isn't that hard to believe? You're more than halfway through with me, and then before you know it, you're going to be switching instructors, and I'll be going away. But what's that?
You're my pencil. Ernie, stop.
Hey,
Get Jupy out of here. Who is Jupy?
it's one of my algebra students.
Can
All
you
right.
kick him out?
Only if it's disruptive. I think his camera's broken too, or his microphone. All right, so congrats on everybody coming to lesson 5 today. So today, good job on making it here today because you guys are going to be so well prepared after today's class. So that's a good part. We're going to learn a lot of stuff today, and it's going to help you a lot to see it first before going in AP Chem. Now, I'm going to be truthful and honest with you guys because I don't like to sugarcoat things, so I'm going to be upfront with you guys. Today's lesson is going to be bad. It's going to be... Today's class, Lesson 5 and Lesson 8 are going to be two of the hardest classes this summer. So today's going to be a bad lesson, unfortunately, but it's going to prep you well for AP Chem. All right, so let me get my camera flipped so I can start doing the problems. I'm going to review a couple problems on the homework real quick. All right, so I took a look at the problems that you guys uploaded, your homework problems. Some of you did very well based on what I saw. Some of us may have been a little confused on this. Can you see this okay?
It's blurrier than normal.
Blurrier than normal. That's wonderful. Why is that blurry? Ethan, you want to come up here and take a look?
I gotta do everything for Gunner.
Video.
Alright, what you want?
Settings.
Oh, shit,
video.
that's why. Stop breathing in the mic, thank you. Let me close on my porn. Those are better.
Is it correct? I think your porn is corrupting your computer. I mean, we can still kind of see it. Sorry for the technical difficulties.
Shit.
Nope.
I think it's close enough.
Alright, well, we'll live with this and I'll play around with it. Sorry. Alright, so this is the homework problem we had last time. Alright, some of us got it perfect, some of us had a couple mistakes on the subscript, so let me do it in front of you guys. So the first thing we always do, remember, is to reverse crisscross this. We bring the coefficients back up. Alright, so now we get Na plus 1, CO3 minus 2, Ca plus 2, and NO3 minus 1. Now, here's the thing I didn't make too clear last class. When we do these problems, we always pair, when we're switching partners, positive has to go with negative. All right? You cannot have a positive with a positive or a negative with a negative. So, in lack of a better analogy, no gay ions, okay? So we're going to switch partners. Na is going to pair with NO3. We're going to crisscross them again, and Ca is going to go with CO3 to get Na, NO3, and Ca, CO3. Let's see, Ca, CO3 to... Oh, did I write the problem wrong? Ca plus 2, NO3, 1. Oh, I think I gave you guys the wrong problem. Oh, I'm sorry. I'll have to relook at that one. I think I wrote the problem wrong for you guys. Oh, no, I'm sorry. No, I just forgot a 2 there. Never mind. All right, so we get Ca2, CO3 2, and then since they're both 2s, they both cancel out. So we get Ca, CO3. Now, we put it all together. We start with Na2, CO3, plus Ca, NO3, 2. And at the end, we got Na, NO3, plus Ca, CO3. Now we have to balance, and the first thing I notice is I have 2 NO2, NO3s here, so I have to throw a 2 on this side. And then I have 2 NAs, but we already have 2 NAs, so the whole thing is balanced. So this is our final answer. Any questions on that? All right. So do be careful on these problems, because as you see how I forgot to draw in one of the charges? That'll mess you up when you're doing these problems. So be careful when you're doing it, check your work, and make sure everything balances. The next problem is I want to quickly go over one of the challenge problems we had. Oh, and it looks like the quality is doing better too, the video quality. Good. All right, so.
Yeah, Steve's probably hopped off the website.
Yeah. Thank you, Ethan. The next problem is we have 0.28 moles of NaCl divided by, we have 0.28 moles of NaCl, and we dissolve it in this much water, and we have to find the molarity. So how we do this problem is, anybody want to guess how we do it? Did anybody get an answer?
Wait, you divide it.
You divide it. Yeah, that sounds reasonable, right? So we have our formula. We already start. We're going to start with our formula for molarity. Molarity equals moles divided by liters of solution. We know the moles of NaCl, so we're going to plug this up here. We have the liters of solution. We're going to plug this down here. So we're going to get molarity is equal to 0.28 divided by 0.25 liters. And when we put that in the calculator, we get 1.12 molar of NaCl. That's the molarity of the solution. Any questions on that? No? All right. So, any questions at all before I move on to what we're doing today? Feel free to unmute if you guys have any questions. I know I'm going quickly because I don't want to keep you guys for too long today. All right, so today we're going to talk about equilibrium. Who's heard of equilibrium here?
Me.
Yeah, you guys, Safik and Aaron were the two hands I saw first. You want to tell me a little bit about it? What does it mean?
Well, it's basically balance, like when everything reaches a point where it like remains in the same state.
Yep. For those of us what about you, Aaron? Do you want to add anything to that?
Yeah, basically what he said, like balancing two things.
Balancing two things? Yep. So in biology, for those of us who took AP Bio, we probably heard of equilibrium. In chemistry, it's a similar definition, but the way we do the math is a little bit different. So since we already know about equilibrium, I'm just going to give a little explanation here. So let's say we have A plus B goes to C plus D. It's a chemical reaction. We have our starting material, our reactants, reacting together, A and B coming together and forming C plus D. Those are our products. But the question is, what stops C from combining again with D and forming A and B again? Actually, the actual answer is, the reaction goes both ways. C and D can actually come back together and form A and B. So the reactions are actually going back and forth. So this reaction up here is the forward reaction. This back here is the backward reaction. And this is something I had trouble understanding. When I first took AB chemistry. How can you have a backward reaction? And it's exactly what it sounds. At the same time, A and B are going to form C and D. A couple other molecules are going the opposite direction. So what happens is in some reactions, the forward reaction happens faster. But in some reactions, the backwards reaction happens faster. But as the reaction keeps going, we get to a point where the reaction levels off. And that's how we know we're at equilibrium. The reaction levels off. So equilibrium, by definition, is when the forward reaction rate, the rate of the forward reaction, equals the rate of the backwards reaction. So that's the first answer on our sheet. And here's another key thing about equilibrium. The products and the reactants, is it okay if I just write P and R to abbreviate? The products and reactants are constantly interconverting. So they're constantly interconverting, which means they're constantly changing back and forth, but the net concentration stays the same. So the net concentration is the same. Now I want to make a point clear, because this is a common misconception. When we say the rate of the forward reaction equals the rate of the backwards reaction, and the net concentration of the products and reactions stay the same, this does not mean that the products equals the reactant. The amount of product does not equal the amount of the reactant. So the amount's not the same, but the speed is the same. The speed at which we're going forward and forming products, and the speed at which we're going backwards and forming the reactants again. But the actual amounts at equilibrium are not equal. So I have an analogy for this. Let's do an analogy. Now, to have this analogy make sense, I kind of have to tell a story quick. So when I was in high school, I had a teacher that had really big stomachs. We were really kind of fat, kind of chunky. So I always told, and I will not name who he was. There's a lot of them that you can guess from. Ethan, don't guess, Ethan. I know what you're going to say. So what happens was, whenever I had group work with my friends, I would always tell them that if they didn't do their part of the work, the teacher would pull them outside and flash his stomach at them. So here's my analogy here is equilibrium is kind of like someone flashing their shirt or their stomach at you. Think about it. The shirt is either up or it's either down. And when they're flashing that quick, it's constantly interconverting back and forth. So you see the stomach, you don't see it. You see the stomach, you don't see it. Okay? So it's happening at lightning speed. The rate of pulling the shirt up is equal to the rate of pulling the shirt back down. Okay? So the speed is the same. They're constantly interconverting. Do we have any questions about that? So it's like two forms that we're converting between. All right. So we understand what equilibrium is now, but then here's the question. If A plus B and goes to C plus D, and just a little notation, to represent equilibrium, that the two reactions can go back and forth, we use a double-sided arrow, kind of like this. It means they go back and forth. If A and B combine to make C and D, but then C and D also recombine to make A and B, how do we know what the amount is of each one? How do I know what the amount of C is if it's constantly going back and forth? And how do I know the amount of A if it's constantly going back and forth? What happens is, to measure that, we have to look at where everything levels off. And to do that, we have to introduce something called K. All right? Anybody ever heard of K's in chemistry? Yeah, I don't think CP and Honors Chem necessarily does it, so we're starting fresh today. I'm going to talk about K. All right, and I believe it's at the center of your page. K stands for the equilibrium constant. Now, what exactly is K? It's a ratio. That's what it is. It's a mathematic ratio that tells us the relation between the amount of products and the amount of reactants. So let's say I have this reaction. The capital letters are the actual elements. The lowercase letters are the coefficients. You remember a couple classes ago when we did the balancing? the formula for K is equal to always the products over the reactants. And when we have a chemical formula like this, this is how we write it. So the products are C and D, right? So we're going to put C and D up top, the concentrations of C and D, over A and B, okay, because A and B are the reactants, C and D are the products. But here's the thing we have to remember, and I guarantee you're going to make this mistake at least once in your chemistry career. You have to raise the concentrations to the exponents, and the exponent is determined by the coefficient in front of the number. All right, so it's C raised to the coefficient in front of C, D raised to the coefficient in front of D. We have A raised to the coefficient in front of A, and B raised to the coefficient in front of B. All right, so the coefficients in front of the balanced equation become the exponents in K. So what does this all mean? It means that we can, if we know the K value, we know the ratios between products and reactants, right? It tells us that the reaction doesn't always split. It doesn't always have equal amounts of products and reactants. Sometimes it leans closer to the reactant side, sometimes it leans closer to the product side. But if we know K, we can guess which one we have more of. So here's a couple of rules that I'm going to show you guys. And if you're good at math, you might be able to derive these here yourself. If K is big, then there's more products at equilibrium. And I believe that's on your sheet too, right down here to fill in. If there's more products at equilibrium, K gets big. And that makes sense, right? Because if we look up here, K is equal to products over reactants. If we have more products, the numerator gets bigger, so K gets bigger. Conversely, if K is small, we have more reactants at equilibrium. And that makes sense because since reactants is in the denominator, if we have more reactants, the reactants number is bigger, and a bigger denominator leads to a smaller K, because you're dividing the same number by a bigger number. Any questions on that? Everybody good? Nobody's lost yet? I found this hard to understand when I first took it. Yeah. You got it, Kevin?
You're kind of just yapping. You're just talking to talk.
All right, well, if no one has any questions, I'll move on. All right, so a couple of other rules before we get to the math here. When we plug in for K up here for C, D, and AB, we can only plug in molarity, not moles, only molarity for K. And we have to use values at equilibrium. Not starting values, not starting concentrations. We have to use the concentrations at equilibrium, all right? So you're bound to, I'm willing to bet everybody makes a mistake at some point in their chemistry career. But if we can remember those two rules, we should be good. So let's look at our first problem. Oh, and I'm going to mention here, there's two types of problems when we're working with K. The first type is solving for K, where you actually have to find what the value of K is. And the other is when you know K already. And you have to find the value of a concentration. I know that makes no sense just writing it out and explaining, but I promise you, I will do problems. And it will make sense. Any questions so far? All right, if we look at the bottom of our first page, let me see. if we look at the bottom of our first page, we see this reaction. X plus 2y goes to 2z. And we're given the container is 2 liters, and we start, and at equilibrium, we have 6 moles of each thing. Notice how we said at equilibrium. That's the key word, at equilibrium. That tells us we can plug directly into K. So, what we have here, we want to find what K is, and the question is, what's K? We're going to start by writing the equation for K, always. So K is equal to products over reactants, right? So Z is in the products, and X and Y are in the reactants. But then we notice Y has a coefficient in front of it, and Z has a coefficient in front of it. Therefore, we have to raise the concentrations of Z and Y to those values. Any questions on how I got that? All right, so once we have this, now we just plug in the numbers. We're told that we have 6 moles of everything at equilibrium, right? So that means we have 6 moles of X, 6 moles of Y, 6 moles of Z. So we just plug in. Oh, I'm sorry, no. We have to find the concentration first. So the container is 2 liters, right? So remember how I said we have to find molarity before we plug in? So therefore, we have to take 6 moles. Remember, because molarity equals moles over liters. So we know the moles, and we know the liters. We have to plug in to find molarity. So we have 6 moles of X divided by 2 liters, which gives us 3 molar of X. And since everything is the same, that means we have 3 molar of X, 3 molar of Y, and 3 molar of Z. Now we plug in. So we get 3 squared over 3 squared. And we plug this into our calculator, and we get K is equal to 1/3. So you see how I've been doing this for 3-4 years, and you see how I almost made a mistake too, plugging in moles instead of molarity. So make sure we always double check to see what we're doing. You cannot plug moles into K, only molarity. Any questions? So that problem's not too bad, right?
Wait, can you go back real quick?
Yeah.
Can you go down a bit more? Just yeah, hold up.
You weren't here last class when we talked about molarity. Basically, molarity is just the number of moles divided by how many liters everything is.
Okay.
Yeah, so we have to take 6 moles of each thing, divide it by 2 liters, and then we get 3 molar for everything. I'm sorry I made that silly mistake there. All right. I know, this is a very dry, boring lesson. Equilibrium. All right, so now our next problem is, it's on the next page. We start with 1 molar of each thing. What is the concentration of CO at equilibrium? So now notice, we're given K already. They gave us the K value, 5.1. But now we have to find the value of something at equilibrium, the concentration. So this is the second type of problem. So earlier when I said there's 2 types of problems you'll get, solving for K, that was the first problem we did. And in that case, you just plug the concentrations in. Now we have this problem. We know the K, but we have to find the concentration of something. And this is where things start to get math intensive. To solve this problem, do you notice how we're only given a starting concentration? In every class before this, we were given the starting amount in grams or in liters, right? So we were able to just do simple stoichiometry. But now we're given a concentration. We can't do the simple unit conversions that we've been doing so far. And since it's looking for the concentration, that also lets us know we can't use the rules we've used in the past few classes. So we have to do another set of rules. And to do that, we have to do a new technique, which is called a rice box. RICE stands for reaction, initial, change, equilibrium. That makes no sense right now, right? But it's easier to explain what it means in a problem. All right?
Of course it's rice, you chink.
I knew you were going to say that. I knew you were going to say that. Some people call it ice box, ICE. Some people call it rice box. I think Miss Powell calls it a rice box. All right. And you know, how do you know when to use a rice box versus when to use the simple stoichiometry you've been doing? If you see concentration, that's a good hint that you might be using rice box, molarity. And if you see equilibrium in the problem, then you're definitely using a rice box. So the key word to use a rice box, when you see equilibrium, and this is where things start to get math heavy. So if you look on the right side of your sheet, I spelled out how to do the rice box problems in a series of steps. I'm going to walk you through how to do it. Step 1. The first step is always to write the K equation. So K equals products over reactants, right? So it equals concentration of CO2 times H2 over H2O and CO. Now, the thing is, I didn't mention this earlier, but when you have an ice box, or when you're writing equations for K, you do not include solids or liquids. So I'll put that on the side. No solids or liquids. In this case, H2O is probably a gas, so we can keep it. All right. How do you know? Well, normally in the problem, it's going to tell you the phases of everything. But since I didn't go over phases, I'm not going to expect you guys to know that. All right. So are we good so far on how I got K? Step 2 is to turn the starting concentrations into molarity. So get molarity. Don't do what I almost did in the last problem, and don't be my dumbass and almost plug moles into the K equation, because that's not going to work. In this case, we're given that everything is already 1 molar, right? So that means we have 1 mole at equilibrium. We have 1 molar, or sorry, at start we have 1 molar of CO, 1 molar of H2O, 1 molar CO2, and 1 molar of H2. At the start, right? Now everything's in molar, but we can't plug into our K equation yet because these are the starting concentrations. We have to get them into equilibrium concentrations. And this is where we have to use our rice box. Let me show you how it's done. So we draw on the side RICE. Reaction stands for the chemical equation. So we write the chemical equation. Initial stands for the initial concentrations. So the concentrations at the start. So we start with 1 molar of CO, 1 molar of H2O, 1 molar of CO2, and 1 molar of H2. All right? Are we good so far? Change. All right. This is step 4. In the change column, we are going to write everything in terms of X. And what happens is, when this reacts, the reactants decrease and the products increase. Do we agree with that by logic? If you start with 2 things and you want to make these, if this goes up, this has to go down. So on the left side, it's going to be minus X, the change that happens. This is minus X. This is going to be plus X. This is going to be plus X. All right. And then we always follow.
Space, bro.
What's that?
You did not give enough space.
Hmm?
You did not give enough space.
Oh, for the problem? You mean I'm at the bottom of the sheet?
Fat.
Ah, well, I'll always go to another sheet of paper. All right. So are we good with how we got minus X? We follow the coefficients when we do plus and minus X. And you'll see that in the next example. Now, E stands for equilibrium. So I literally write everything that just happened. So equilibrium is 1 minus X for CO. It's 1 minus X for H2O. It's 1 minus X for CO2, and it's 1 minus X for hydrogen. Are we good? Let me know if I need to repeat anything.
Wouldn't it be 1 plus
Oh,
X?
sorry, 1 plus X. Yes, 1 plus X. Good catch. I just saw that. You don't get step 3. So step 3 was to plug into the initial column. So this is the initial column right here. So it says we start with 1 mole of CO, 1 molar of H2O, 1 molar of CO2, and 1 molar of H2. So we just plug the 1 into the initial column. Does that kind of clarify? I meant the change. Yeah, the change step is the hard part. The change step means that every time this reacts, this decreases by some number. CO decreases by some number. We don't know what that number is. It's X, but we're going to solve for it. H2O decreases by some number. It's minus X. But then that's the reactant side. On the product side, every time this decreases by some number, this increases by some number. So it's plus an X.
I have a question.
Yeah, go ahead.
So in the change step, would the X ever have a coefficient other than 1?
Yes, exactly. That's exactly what's going to happen in the next problem.
Okay.
I was going to wait until the next problem to mention it, but since you brought it up, if there was a 2 in front of this, let's say it was 2 CO2, then it would be plus 2X because there's twice as many. Mm-hmm.
All right, thank you.
All right. Anybody else have any questions? All right. So, step 6. Plug everything into K. So we know that K is equal to CO2. I'll just write it again. H2 divided by H2O and CO. So now, remember what I said about K. We can only plug in equilibrium concentrations, which means the E column, right? I only care about this E column now. I can cross everything out. I only look at the E column once I get to step 6. So now I plug in for K. K equals products over reactants, so 1 plus X over 1 plus X over 1 minus X, 1 minus X. Are we good? I took the values and plugged them in terms of X. But wait! We were told at the beginning of the problem that K equals 5.1. So we set this equal to 5.1, because this is K. This whole ass thing is K. And now, guess what we do? We solve for X. Oh, I can hear the moans already. What the fuck are we doing? We're solving for X. Okay, I'm going to give you guys a few tricks.
Bro,
So
I'm ugly. Fuck you.
Kevin's already got the middle finger. All right, so you see how this is the same and this is the same, the top and bottom? So do we agree I can change this to x, 1 plus x squared over 1 minus x squared? Did we agree with that?
Yes.
5.1. Now, since the top and the bottom are both squared, we can just square root the whole thing, right? And we get 1 plus x over 1 minus x equals, I'm going to plug this into the calculator, 5.1 square root equals 2.258. So you guys have taken algebra 2, so you probably know how to solve this. Now we just solve for x. So I'm going to multiply both sides by 1 minus x. Equals, this is going to get messy. I'm going to distribute this and combine terms, but to save you guys time, x equals 0.386 molar. All right? Any questions on how I did that? It's just algebra.
I ran out of space.
Yeah, I had to really write it small when I did it on mine.
Bitch.
But that's not our final answer though, right? Because the original question asked, what's the concentration of CO at equilibrium? We only found X. But here's the thing. If we look back at our ice table, do we see how CO at equilibrium is equal to 1 minus X? And now we solved what X is. So now we just have to plug it in. So we got from our ice table that CO at equilibrium is equal to 1 minus X. So I take this for X and I plug it in, 1 minus 0.386, and I get the concentration of CO at equilibrium is equal to 0.614 molar. That is our final answer.
Know yourself.
Any questions? So what does this mean? This means that this reaction is going back and forth, back and forth, back and forth. But at the point where it levels off and reaches equilibrium, the concentration of CO is that. The net concentration. So my example for equilibrium is, let's say you have, 10 cookies. And every time you eat 2 cookies, you make 2 cookies. The net concentration doesn't change, right? Although sometimes after you eat the 2 cookies, you have 8. But then once you make the 2 more cookies, you have 10 again. So even though it changes back and forth, the net concentration does not change. Any questions? Let's look at the next problem. We have N2 plus O2. And this is a problem I changed just yesterday. Is that the correct? Somebody confirm, because it's different on mine. Is this the correct formula?
Yeah.
Yeah? All right. And K is 0.1. And we start with 0.44 moles of N2 and 0.44 moles of O2, right? And we want to find the concentration of NO at equilibrium. All right, so here we go. Step 1. What's step 1 again? Somebody shout it out.
Write the equation.
Write the equation for K, right? Write K. So K is equal to products over reactants. So it's going to be NO, concentration divided by N2, and O2. But wait! I look up, and I see there's a coefficient. There's a 2. Which means I have to raise NO to the second power. Step 2. What's step 2?
Find the molarities and then plug them in.
Molarity, yes. Perfect. So we start with 0.44 moles of N2 and 0.44 moles of O2. Molarity equals moles over liter, right? And we're given that the container is 2 liters. So we have 0.44 moles of N2 divided by 2 liters and 0.44 moles of O2 divided by 2 liters. So now, we plug this into the calculator and we get 0.22 molar N2 and 0.22 molar O2. Any questions? Now, step 3, 4, 5. 3/4/5 all together. This time is coming. The rice box time. R-I-C-E. What does that spell? Kill yourself. No. Rice, all right? So we start by writing the reaction. N2 plus O2 goes to 2NO. Step 3. We're going to plug into the initial column. Because we start with 0.22 molar N2 and O2, we're going to put 0.22 in here and 0.22 in here. And we start with 0 NO, right? Because we weren't told we had any, so we start with 0. Now, this is where shit starts to come apart and heads start to fly and tears start to roll. Because I've seen people cry at this. The change column. On the left side, the reactants is going to decrease. So it's going to be minus X. But wait, on this side, we know we have to add. But there's a 2 in front of the NO. So it's actually plus 2x. So you follow the coefficients. If it's a 2, it's plus 2x. Any questions? And now at the equilibrium step, the E is going to be 0.22 minus x in the N2 column. 0.22 minus x for the O2 column, and 0 plus 2x. That's just 2x. Any questions? All right. So now.
Wait, why is it 0 plus x?
Because we started with 0 N2. 0 of NO. Because the problem didn't give us a concentration of NO at the start.
I knew that.
Great. I knew that too. Bitch, yeah, I know. This is whoever made these problems. Like, who comes up with this? Like, who just sits in a room by himself and is like, oh, this is how we measure equilibrium concentration. I bet he wasn't married either.
I feel like you did that.
I'm not smart enough to get. Look at this. I almost put moles into K. I'm not smart enough to make this.
Perfectly, man.
All right, so step 6. What's step 6?
Take the knife and hold it to your wrist.
That was me when I first learned this. True story. Nah, I'm exaggerating.
Yo, wait.
I do not.
You know, which one?
Don't look at what Kevin's doing. News coming. All right. Step 6 is to plug in K. So from earlier, we have K is equal to NO squared over N2 O2. So now we're going to plug in the values from the equilibrium column. Oh boy. Equilibrium only. All right, so I don't care about what happens before that once I get to K. So I have 2x squared over 0.22 minus x times 0.22 minus x equals. Remember how at the start they gave us that k is equal to 0.1 equals 0.1. And now what we do is we solve for x. So 2x squared, I'm going to write the bottom as 0.22 minus x squared. I'm going to square root both sides. I get 0.1 is equal to 2x 0.22 minus x. And I know you guys can solve for x because you've all had algebra 2. I'm just going to give you the answer.
Do this.
You can see me after class. Does anyone want me to solve the full thing out?
No.
No?
Yes, please.
Yes?
Jerry.
Jerry, are you taking this class, Jerry, or did Kevin?
No. I am taking this class.
All right, so I'm going to multiply both sides by 0.22 minus x. I'll only show this once. I get x equals 0.1 times 0.22. If you know how to solve for x, don't mind what I'm doing. This is only for demonstration purposes. Man, you really had to make me do this, Jerry.
Jerry gone.
I square root that, and then whatever it is, x equals 0.03. You can see me after class if you want to see me see how I solve for x. But it doesn't ask for x. It asks for NO at equilibrium. So we look back at the ice chart. NO is equal to 2x, right? So NO is equal to 2x, which means we take 2 times 0.03, and we get NO at equilibrium is equal to 0.06 molar. Any questions on that?
Justin,
Yeah.
when I did the square root of 0.1, I got 0.316228 on my calculator.
That's correct. Yeah.
0.1, right, for the square root?
Yeah, sorry. I was doing it too quickly, and then I forgot to write it. But as long as your algebra is correct, you should get x equals 0.03.
Okay.
Yes, but I noticed I forgot to square root. That's what happens when you try to do it fast on camera. Any other questions? I don't like these problems, but I hope my explanation makes sense. I want to give you guys a quick note, a quick trick on these problems. Let's say I get this. I get to a point, and it doesn't matter how I got here. Let's say I got this, and I have to solve for x in a hypothetical situation. The only way to solve for x is using the quadratic formula, right? Because when I multiply this over, I have an x and an x squared, so I need the quadratic formula. Now, is there anybody here who really likes math? All right, I like math too. You're not going to like me, what I'm about to do here. The way it's written now, we have to solve it using a quadratic. But what you can do, and this is what they teach you to do in AP Chemistry, you just get rid of this x. Forget it's even there. And now you solve this without using a quadratic. Because now there's only an x squared, and you can just square root the whole thing once you isolate x squared. So that's how you do it. Just get rid of that extra x. And they let you do that on the AP Chem exam.
Why?
Because in these problems, x is so small that it makes very little difference. It's like 0.001 difference or whatever. All right?
So basically, x is so small you can treat it as a constant.
Yeah, pretty much. Pretty much.
Okay.
Or we just ignore it altogether.
Okay, fair enough.
All right, so any questions before all right, the meeting is going to kick me out in 5 minutes. There's a little more material I have to go over. That'll take about maybe 10 minutes. I will post an extension link, but if you are too busy, it's perfectly fine if you can't stay after, okay? But I'm going to see how long I can get. I'm going to talk about Le Chatelier's principle. So it's on the next page. All right, so we look on that. What do we see next to Le Chatelier's principle? Look at that. Does that look familiar? We're talking about Le Chatelier's theory. Now, in theory, Le Chatelier was a French chemist, but I thought that in this case, this made such a better analogy rather than Le Chatelier. So, let me see. Get my notes. All right, it's enough of that. The camera's gonna cut me off. Oh shit! Sorry. Oh, I forgot there was a Chinese person in this meet. Oh boy. Oh boy. All right, so. All right, I'm gonna try to get as far as I get before the camera cuts me off. All right, Le Chatelier's principle says that a chemical reaction wants to be level. It wants to be even and level, which means if we are at equilibrium and we do something to mess up the equilibrium, let's say this is floating happily in equilibrium. If we dump in some more C, a more amount of C, do you agree that that messes up our equilibrium? Le Chatelier's principle, or at least what our chairman Mao here is saying, is that the reaction will naturally move to compensate for that change. And this is kind of like, actually, you know, I'm going to stop this call right now before I get too into it and it kicks me out. I will send an extension link, okay? Just so the camera doesn't cut me half sentence.
Yeah, I'm leaving out, bro.
All right. Just wait for anyone who wants to join. I'll let them in. Sorry this lesson took so long.
Justin, am I on the list?
Well, yeah. I got maybe 10 more minutes of lesson worth. All right. So Le Chatelier's principle says that I'll give it a couple more minutes. Or another minute.
Can we wait for Hui to join the call?
I thought you wanted the algebra kids out.
Yeah.
Should I start the music again?
Yo, what's that song called? I gotta add it to my Spotify. Nice volume, nice volume.
You know, I almost got in trouble once for drawing a picture of Mao Zedong on a whiteboard in college.
Dumbass.
I don't think the international Chinese kids were too happy. Alright, that's enough of that. Now, I just said that Le Chatelier's principle says that when we're at equilibrium, if we mess up our concentrations at equilibrium, the reaction will naturally compensate for it. Which means that, let's say, I will draw this out again. Actually, let me draw it a little lower. Let's say I'm going to pretend to draw little molecules, okay? If we dump in, so you see how there's one of A, one of B, one of C, one of D? Let's say all of a sudden we dump in some extra A. We just messed up equilibrium. What Le Chatelier's principle says is that if we dump in more A, we're going to use this extra A we just dumped in. And we're going to make more C and more D in order to make it level again. So an analogy is taking from rich and giving to poor. Taking from rich people to give to the poor people. So A is... oh, I just closed it. Darn, that would have been a perfect opportunity. So A is super rich and C and D are super poor. But then what Le Chatelier's principle says is that we're going to take money away from A and give it to C and D. All right? In other words, you can think of it as spreading it out. We want to spread it out. Share the wealth.
This is down to legs.
Yeah, you can think of it like that from last week's analogy. All right, so let's look at our example. A plus B goes to C plus D. The first one, let's say we increased A. So let's say we start with this much. And we increase A. See how I'm drawing extra A? What Le Chatelier's principle says is that since we have so much more A, we're going to go and make C and make some more D. So then the final result might look like this. I'll put one here. I hope the colors show up okay. You see how we took some of A's stuff and we moved it over to C and D? Now everything's pretty level again. It's not perfect, but it's more level than it was before. This is called a right shift. Because you see how the reaction moved right? We took some stuff from A, we mixed it with B, and we produced more C and D. That's called a right shift. Because the whole reaction moves to the right. Any questions on that? I didn't get this the first time I took chemistry.
Because you're stupid.
Nah, because nobody explained it in terms of Mao Zedong.
That's crazy.
Let's look at the second example. If we increase the amount of C, so you see how there's so much more C? We're going to take this C and we're going to make more A and B. We're going to go back the other way. So the final result might look like that's the final result after we shift the equilibrium. See how we took a lot of C, a lot of money from C, and we spread it out to the poor? So now it's more level. It's more even. It's not perfect, but it's more level. This is called a left shift because we took products and we went backwards to make more reactants. We moved the entire reaction to the left. So that's how you do these problems visually. I'm going to show you guys a shortcut. This is how I do it, at least. We start with this, at equilibrium, and we're told that we increase the amount of C. So immediately I just draw an arrow showing that the C side got blown up. So whichever side gets blown up, it moves in the other direction to make more
square.
Who got that analogy? I don't think anybody got that, Ethan. Your comment.
This isn't. They don't have VPN.
So we increased C, we blew up C, and we moved to the left. So that's a left shift. Any questions on that? It's a tricky concept. The next question. What happens if we decrease C, if we decrease D? So let's say we just got rid of one of these things. Someone want to guess what's going to happen? We took away one of these things, right? So A and B, we're going to take some from A and B, and we're going to give some to D. So this D basically just, I don't know, he lost his wallet. So he has less money. So we're going to take Le Chatelier's principle, and Mao Zedong is going to come and knock on A's door and knock on B's door and take some of their money and bring it over to D. So the final thing might look like this. We took something from A and we gave it to D. And then the last example, if we decrease B. So if we decrease B, B just lost its money. So we're going to take something from the other side, the product side, and we're going to move it over. We're going to take money from C and D and we're going to give it to B. So that is a left shift. Because we're taking product and we're making more reactants. Any questions? All right, so let's look at a real example. 2SO3, 2SO2 plus O2. So the first question is, we add more SO3. Which way will it shift? If we add more SO3... Right, because we blew up the left side. This totally got blown up. Ethan, your pens don't work. This got blown up. So we have to move it right. So this, if we add more SO3, that's going to be a right shift. What if we take away O2? If we take away O2, O2 just lost some of its money. So Mao Zedong is going to go to the opposite side, onto the reactant side, knock on his door. It's going to take money away from SO3 to make more O2. So that's going to be a right shift because we're taking reactants and we're making more products. The last thing is, what if we add more SO2? Anyone want to take a guess?
Is it left?
Why?
Well, because it's on the same side as O2.
Yep, so we blew up SO2, and we want to distribute the extra money, so we're going to move to the right. So that's a right shift. All right, so I know I promised 10 minutes, and that's pretty much the end of the chemistry section. But if you have to go, that's okay. But I want to spend a couple minutes talking about an application to this. This is the challenge. Do you see on the next page where it says a challenge problem? So this is an interesting bio application. So why do we care about equilibrium? We've been talking about it for the past hour. Why do we care? What happens is, it's used a lot in biology. So in the human body, there is something called the bicarbonate buffer system. All right. And it looks like this. It's an equation in equilibrium. It goes to the right and it goes to the left. And what this does is it maintains your body's pH. For those of you who took bio, this might look familiar. So my question to you guys is, here's question 1. If we increase CO2, what happens? In the body, when the tissues are at exertion, when we're exercising, they produce CO2 as a waste product. So CO2 is going to increase. So what happens to CO2? Or what happens to the equation when we increase the CO2? I want to see if I can make a poll for this. I don't think, no, they got rid of the poll thing. What do we think? We can, somebody unmute or put it in the chat? What's going to happen?
Right shift.
Right shift, right? So what's gonna? So we know it's gonna shift right. It's gonna be a right shift. What's gonna happen to the amount of hydrogen?
Increase.
Yeah. So H is gonna increase. And now you guys don't have to know this, but when hydrogen increases, the blood pH decreases, and the blood gets more acidic. But you don't have to know after this class. Now that's why equilibrium is so important, because in the human body, we can't just keep producing too much of one thing. We can't have too much CO2 in the body. So therefore, equilibrium gives it another path to go in the other direction, so it doesn't all just build up. We don't build up too much CO2. That's the purpose of equilibrium. And then question B is, let's say we increase the amount of H. What happens? What do we think is going to happen to the CO2 levels? So we just blew that up.
CO2 would increase.
CO2 would increase. Is it a right shift or a left shift?
Left.
Left shift, right? And the CO2 increase. And do you think that would make you breathe more or breathe less? It actually makes you breathe more.
More. Yeah, more.
Yeah, so breathing will go up too to get rid of that CO2. So that's the application of what we were working up to build towards today. We know that equilibrium is important because in biology, it allows us to move back and forth. So we never end up with too much CO2 or too much hydrogen. If there's too much of one thing, equilibrium gives us a path to create another thing. So it doesn't just all build up. So that is the end of the lecture today. There's the worksheet problems if you guys wanted to stay and do some. Otherwise, you guys are totally free to go. I'm sorry I kept you for this long lecture. I know today's lesson was a pretty boring lesson, right?
Yeah, fuck you.
Yeah.
It's not as interesting as some of the other lessons we've had, but Hopefully my explanation made sense. I know we covered a lot today. All right, if that's all, you can stay and work on the worksheet, and I'll give you guys the answers to that.
Background music for the next lecture. That would be very nice.
What's that? What's
You
that?
should make the music you played the background music for the next lecture.
Then, I wouldn't want to like offend Aaron or anything like that.
Bro, I'm not even Chinese.
Yeah, he's North Korean.
Alright, bro. Justin, that was even more racist. Than
Oops.
Mr. Kim's got a grip on Aaron, bro.
Oh wait, and my algebra kids are still here too. Oops. I'm sure one of them is Chinese.
Hui.
All right. If you guys want to stay and work on the worksheet, that's okay. Otherwise, if you guys want to head off, that's perfectly fine. But let me know if you have any questions if you're doing the
Can I
worksheet.
stop the recording?
Yes. Yeah.